Ladies and gentlemen, it's my honor to give this talk entitled Springproofs, Efficient Inter-Product Arguments for Vectors of Arbitrary Length. The first author is Ning Zhang, who implements the Springproofs, and Dr. Ming, the presenter today. Professor Liu and Wang are my colleagues. This is the poster question and answer, including Ning Zhang and me. This is the outline of my talk. First, I will introduce the motivation and the background of our research work. Afterwards, I will present our main scheme, the Springproofs. Finally, I will provide some experiments show merits of our scheme. It is well known that blockchain has been widely used in cryptocurrencies, decentralized finance, lotteries, and many other areas. However, because the data has been shared publicly and is transparent to anyone, so privacy becomes a big issue. To overcome this problem, so zero-knowledge proof has been proposed to solve this problem. This is a typical example of Alibaba's cave, a game between the prover and verifier. Originates from zero coin and Zcash, zk-SNARK, zero knowledge succinct non-interactive arguments for knowledge has been a popular solution, like EasyCheck, the Polygon sidechain solution of Ethereum, and Tornado Cash. This supports privacy protection on general circuits, but for some specific arithmetic circuit, it could be more efficient. Like the range proof, actually the prover needs to assure the verifier private input is within a range without actually revealing the real value. It already has applications in Monero Cash, Zeta, and Green, and many other applications. The core technique of range proof actually is the IPA, the inner product arguments. It is a kind of relation that the private input AB, which is a vector size of n, we may regard it as witness that they satisfying commitment and the interproduct relation, where G and H are over the group G with dimension n. It has the advantages like the logarithm of size of input, supports aggregation, batch verification, the transparent setup. Therefore, it has wide applications in confidential transactions and has been deployed in smart contracts. There are many existing works discussing on this, like the Bliss proofs, GIPN and shell proof, and many others. For the triple IPA, prover needs to send A and B of size n to the verifier. This is 2 n-filled elements in total. And for the basic Bliss proofs, the prover can reduce by folding. In this way, he sends L and R belongs to group elements. So in this way, he only needs to send 2 group elements and unfilled elements. Using this idea iteratively, which is proposed by Bones and Bootle. So finally, the prover needs to send 2 log n grouped elements and 2 filled elements. However, this requires the length of the vector to be a power of 2. So normally, we need to do padding, which may bring additional overhead. Can we improve on this? Therefore, we propose the Springproofs. The main idea is to divide the indexes into S and T, where S is sent separately and T is for folding. Then we iteratively use this relation for reduction. And finally, we need to send in two M group elements and two field elements. This is the algorithm of Springproofs, where a scheme function is adopted to decide whether we do padding or compression at each iteration. We prove that the Springproofs without padding is better than the version with padding, and the Springproofs without padding achieves the optimum. This is the comparison of computational complexity for bleed-proofs and Springproofs. This is the unit operation. You may see that regarding the verifier, so because this is a Gaussian sealing function, so the verifier can achieve almost twice speed up when n is a little bit larger than a power of 2. For security consideration, the completeness is straightforward, and we can construct extractor to achieve the soundness. For zero knowledgeness, we include the blind factors here. If a spring-proof based unfolding procedure satisfies the blinding factors is uniformly identically independent distributed before and after folding, and the folding procedure is host verified zero knowledge, then the Springproof is HVZK. Now we give experiments on aggregated range proof performance and the size of proof. The size of proof of bleed proofs and spring proofs are the same. Regarding the proof generation and the proof verification, the spring proofs are continuous and can achieve even twice speed up. And this is the hardware and the software setting. Next, we consider the generation and verification time for Monero transaction. It is illustrated that the spring proofs-based Monero transaction is around 60% of that of bleed proof-based version, when the number of outputs is 9. Moreover, we consider batch verification time of 100 Monero transactions. As illustrated in this figure, the spring proofs can achieve around 20% advantages as that of bleed proofs. Also, we consider the generation and verification time for SHA-256 circuit. It is shown that the spring proofs can achieve about 60% of that of bleed proofs. Besides, we consider the case of membership proof for Merkle tree, and the spring proofs based version is still better than that of bullet proofs. Finally, we consider arithmetic circuits on some frequently used statistics like the expected value and the variance. Not only the spring proofs is better than bullet proofs, but also with the BP format and R1CS format changing, we shown that the Springproofs version performs better than that of GOS 16, a general zk stock version. Regarding the variance, it is shown that when the number of samples is in this range, the performance of Springproofs is better than Bulletproofs and the Gross 16. To sum up, we have the following contributions. First, we propose an IPA for arbitrary vector lengths, and the Springproofs avoid the need for zero padding. Also, SP is almost twice as fast as BP when the vector length is slightly larger than power of 2 for range proof. Finally, we demonstrate efficacy in various applications, including range proof, Monero transaction, and privacy computing. Thank you for your attention. If you have any questions, you may write to the following email address.